All right, so let's go ahead and finish up this chapter. So, in the last little bit, we talked about sort of the forces at play essentially inside of matter. So, inside of liquids, solids, and gases. So, we discussed that, in a gas, we have very little interaction between molecules or particles, you could call them. In a liquid, we have a lot more. So, now we have particles or molecules that are attracted to each other. They have forces that hold them together. It's very difficult for individual molecules to escape a liquid. Okay, they can move around freely between each other, but they have some influence on, how much movement takes place. In other words, they have interaction with each other. We have to put a lot of energy in to sort of remove an individual molecule. And then we talked about in a solid, they have even less freedom, so very little freedom to move. You could say zero, but we know that they're vibrating still. So there is some movement there. And then we said that in order to actually break a molecule away from a solid, you have to actually destroy the piece of the sample of whatever you're talking about. So you have to actually physically break it. Whereas you could melt it and change it back to a liquid, and then you could heat it up even more and maybe change it into a gas. And we talked about how some forces are stronger than others. So for instance, your dispersion forces are our weakest forces we talked about. Okay, so all matter has these. So it's the weakest force that we know of between two molecules. And remember, these are intermolecular forces, so they're between two different molecules. Then we talked about dipole-dipole, so this can only happen with polar molecules. We talked about hydrogen bonding, which is basically a special type of dipole-dipole, where we have to have an electronegative atom, like fluorine, oxygen, or nitrogen, with a hydrogen bonded to it, and then we have to have a lone pair on the fluorine, oxygen, or nitrogen. Okay, and then lastly, we talked about ion dipole. Okay, so this occurs when we have an ion, either positive or negative, and we have some polar molecule surrounding it. Okay, so now that we know sort of what influences these properties, let's talk about the actual properties themselves. Okay, so, and we'll cover these, I think there's a handful of them, and we'll cover them one by one, and we'll talk about what influences them and how the trends go in terms of heating and cooling and this kind of thing. So the first one is viscosity. So viscosity is the resistance of a liquid to flow. So in other words, it's something with higher viscosity will have less flow. So it's more resistant to being poured. So the best way I can sort of explain to you to remember this is that something like honey, for instance, has a very, very high viscosity. So I think that's one of the touchstones to kind of keep in your mind with this. So if I can't remember what's a high viscosity and a low viscosity, hopefully you can remember that I said honey has a high viscosity. And if you know honey as resistance to flow, then you'll remember, okay, yeah, so something with a high viscosity resists flow a lot. Okay, we measure this in units of poise and most commonly in centipoise. Okay, so if we take a look at just some alkyl chains here, so starting from pentane down to nonane, and we look at their viscosity. Okay, so if we take a look at their molar mass, we're increasing molar mass from top to bottom. So obviously every time we add a carbon, we get a little bit heavier. And we see that these have a chain-like formula. So remember we talked about being able to stack chain-type molecules. Okay, and if we look at their viscosities, we see that pentane has a relatively low viscosity, so 0.24 centipoise, and we increase every time we add a carbon. Okay, so let's think about this. So what else did we say increases every time we add a carbon? Let's think about the forces in play here. So I don't have polar molecules. Just by definition, I know hydrocarbons are nonpolar molecules. I don't really have, there's no ions to speak of. Okay, there's no hydrogen bonding. So the only thing I have here is London forces. So what do we say increases, well, how do London forces increase? So we know that if we increase molar mass, we increase our London dispersion forces, and also if we increase our surface area, our surface contact. Okay, so this statement up top in the blue box, so stronger intermolecular actions gives you a higher viscosity, which should sort of make sense. So if we're trying to peel a molecule away from the other, so remember in a liquid I said they have movement, they can like slide past each other. So think about that. So thinking about being in a crowded room, maybe at a concert, and trying to get up to the front. Okay, so you're trying to slide past people. Okay, so the more more resistance you have, the harder it's going to be for you to get up to the front of the concert. Okay, so that's the same thing with viscosity. So the stronger the attraction is between the individual molecules, the harder it's going to be for one to slip past the other, and so the harder it will be for the liquid to flow. Okay, so if I have strong interactions, it's harder to flow. It's maybe like trying to get away from your friends at a concert. Maybe that's a better analogy. Okay, so the stronger they're pulling you back, the harder it'll be for you to get away. Okay, so if I have stronger forces, then I have a higher viscosity. Okay, so we know that if we have stronger forces, we have higher viscosity, but let's look at how temperature affects viscosity. Okay, so here we have viscosity on our y-axis and temperature on our x. Okay, so as our temperature increases from left to right, notice what happens to our viscosity. Okay, so you can see it's trending basically downward. Okay, that's a terrible arrow, but you can hopefully get my meaning. Okay, so viscosity goes down as temperature increases. Okay, so say at 20 degrees, here we have water. Okay, so this is a good touchstone, by the way, if you're looking at what's a high viscosity or a low viscosity. So water at around room temperature has a viscosity of 1. Okay, and as we increase that temperature, you can see our viscosity goes down. Okay, so all the way down to about 0.28. Okay, so as we increase temperature, our viscosity goes down. And why would that be? Well, we're putting more energy into our liquid. Okay, so remember that it takes energy to help those molecules start to break away. So this is like giving enough energy for them to move around and slip by each other, but not enough to actually break out of the liquid. Okay, so increased temperature, viscosity goes down. Increased molecular forces, strong or higher viscosity. I hope I said that right. So increased temperature, viscosity goes down. If I increase my molecular forces, my viscosity goes up. Okay, so the best analogy here is either heating up honey to put in your tea maybe in the morning, or at night maybe, or heating up syrup to put on your waffles or your pancakes. Okay, so we know that these are really viscous substances. They have high viscosity, so if I put them in the microwave for a second and I heat them up, or on the stove maybe, I know that they flow a little more easy, right? So as I increase temperature, I lower my viscosity. Okay, the next one, surface tension. So we'll start out with a definition. So surface tension is the property of liquids that results from a tendency of liquids to minimize their surface area. Okay, so a better way of thinking of this is maybe this is a measure of how attracted a liquid is to itself. Okay, so stronger intermolecular attractions, stronger surface tension. So again, as intermolecular forces go up, so does surface tension. Okay, so this is kind of a cool thing here, that where if you put a sample of water into a low gravity environment, like if you were an astronaut, okay, so the water will actually form a sphere. It'll actually minimize the surface area with air essentially, and maximize its surface area with itself. Okay, so as long as there's no gravity, water would just be a sphere. Okay, so if we take a look at this, so molecules or atoms on the surface feel attractive forces from the sides and below, and thus are drawn towards the liquid. Okay, so if when we're talking about the surface, we're talking about this area out here. Okay, so everything on the outer side of the water sample. So you can just envision these as just being molecules of any liquid sample. It doesn't really matter. Okay, so if I'm, for instance, this particular molecule, I feel forces pulling me this way, this way, this way, and this way. So there's nothing pulling on me in this direction. And the reason that is because there's simply no molecules there to be pulling on me. Okay, so in other words, I'm interacting with my neighbors, and when there's not a neighbor, there's no interaction. Okay, and if we look at that versus a molecule that's more towards the center, so you're feeling attraction, or this molecule is feeling attraction, in all directions. So it's being pulled in all directions evenly, essentially. Okay. So what this results in is when we're over here towards the edge, see, we're being pulled in several directions as well, but nothing towards the outside. Okay, so what this results in is basically surface tension. Okay, so the molecules are being pulled down into the liquid versus there's really nothing pulling them away from the liquid. Okay, so that's what gives you this high surface tension, where you almost have, for something with high surface tension, so you have almost like a glass surface. So this is what gives bugs that can walk on water the ability to do this. It's what make very light objects like a needle or a paperclip float on the surface of water. Okay, and so there's an experiment that sometimes is done in general chemistry where you take a look at different liquids and you look at their surface tension. And if you have something, let me just find a slide where I have some blank space here. Let's look at this one. So if I have something like water, for instance, if you ever look at a water droplet and you were to get down eye level with it, you'll see something essentially like this. Okay, and then if I look at something that has really, really high surface tension, it'll be almost a sphere. So if I have a table here, okay, and then if I have something with really, really low surface tension, it'll be more almost just like a puddle. Okay, so if that's my surface, my water. So what I'm saying is, the stronger that these molecules are pulled inward, you get more of a curve like this rather than like this. Okay, so that's a result of surface tension. Okay, and again, that's what gives bugs and things the ability to walk on water like this, because the surface tension is very, very high. And if we take a look at surface tension versus temperature, okay, again, as we have surface tension on our y, temperature on our x, as we increase temperature, so from left to right we increase temperature, our surface tension goes down. Okay, so stronger intermolecular forces give us higher surface tension, and as we increase temperature, we lower our surface tension. Basically what you're doing, if you think about it, is you're just giving the molecules more freedom. So just like with viscosity, anytime you put energy in, molecules get more freedom, and so things like surface tension, viscosity, these things go down because they can move around easier. Okay? Okay, so the next one we'll look at is surface forces. And we can break these down into two categories. So we have either the adhesive forces or the cohesive forces. Okay, the adhesive forces are the intermolecular forces that bind surface molecules to another surface. So this would be something like a container, or it could be your graduated cylinder, I think is a good way to think about this, or a burette even. And then we have cohesive forces. Okay, so these are the intermolecular forces that bind surface molecules to one another. So adhesive, you could think of like like additional, like it's something else. That's a good way to think about it. Or you could think like adverse, like they're against each other. Okay, so it's like they're against their own molecules and they'd rather be with something else, or with another object. Okay, or you could think of cohesion, like like we're all together, like we're working together. Okay, so cohesion is attraction to itself. Adhesion is the attraction to something else. And if we just take a look at two examples here, so if we increase the attractive forces in a molecule, okay, then our cohesion forces dominate. So in other words, this is when we have high IMF, and this is if we have low. Sorry, I can write that a little bit better. This is if we have low IMF. Okay, so if I have high attractive forces, cohesion dominates. If I have low attractive forces, adhesive forces dominate. Okay, if we just take a look at two examples, so we have water, which has very high cohesive forces in its own right. Okay, but if we take a look then at mercury, it's even higher. Okay, so mercury has a higher attractive or has higher attractive forces compared to water. Okay, and that's due to the metallic bonding versus the H bonding. So hydrogen bonding, we know very, very strong cohesive forces, or just IMFs. Okay, but mercury has even stronger attractive forces. So let's take a look at how that results. Okay, so when you put a liquid into something like a graduated cylinder or just maybe a thin tube, you get what's called a meniscus. And this can either be a positive or a negative meniscus. So it can either go up or down, in other words. Okay, and the meniscus is the shape of the liquid, or the shape of the liquid surface, which is due to the competition between adhesive and cohesive forces. Okay, so when we see a meniscus, we have those two forces fighting each other. Okay, so it depends which is dominant based on, will tell us what type of meniscus we get. So either get the one that goes up or the one that goes down based on if the liquid is more attracted to itself or if it's more attracted to the container. So remember we said that water has very strong cohesive forces or very high attractive forces, but compared to mercury, mercury has much higher attractive forces. So what this results in is, as you can see, the meniscus of water is concave. Okay, because the adhesion to the glass is stronger than the cohesion to itself. And if we take a look at that and compare it to mercury, we see that we have a convex meniscus in this case. And again, that's because the cohesion to itself is stronger than the adhesion to the glass. So mercury is more attracted to itself than it is to the walls of the glass tube, whereas water is more attracted to the glass tube than it is to itself. Okay, and that results as either a concave or a convex meniscus. Okay, so again, higher attractive forces will let cohesion dominate, lower attractive forces will let adhesion dominate. Okay, and together, these can result in capillary action. Okay, so capillary action is the ability of a liquid to flow up a thin tube against the force of gravity. Okay, so there's something called capillary tubes that are often used in the lab for if I need a very small amount of a liquid or a liquid sample. Okay, and you can blot them on TLC paper. Maybe you'll do this if you go into organic. Okay, but this works basically through sort of a balance between cohesion and adhesion. Okay, so capillary action is a result of the cohesion and adhesive forces working together. Okay, so cohesive forces hold the liquid molecules together, and the adhesive forces attract the other liquid molecules to the tube's surface. So it's sort of like it clings to the surface and it pulls it up, clings to the surface and pulls it up. So those two fighting together, or those two working together, actually cause the liquid to climb. Okay, so this is like if you've ever dip your straw into your drink and put your finger over it, you'll notice that the liquid is still stuck inside. That's mainly due to the vacuum, but the actual climbing of the liquid up the straw, okay, that's due to capillary action. And the smaller the tube you have, the more narrow the tube, the higher the liquid will rise. So something like a straw is pretty fat compared to a capillary tube, but you do see some capillary action there. But a capillary tube is very, very narrow, okay, so you see a lot of capillary action. But basically, both forces compete together to fight against gravity, and it will cause that liquid to rise up the tube. Okay, so that was our properties of liquids, and we will be moving on to some phase changes. And we'll mainly be looking at phase changes in terms of entropy. Okay, so in terms of energy transfer. So here we have just a basic sort of phase, not a phase diagram, but sort of an energy diagram where we have energy on our y-axis, and then we have three states of matter. So we have solid, liquid, and gas. And what we want to look at is what happens, for instance, if we put energy in. So what do we have to do in order to melt a solid? Okay, and melting is often called fusion. More commonly, we call it melting. Okay, so what would the energy change be? So the delta H, so let's go all the way back to thermodynamics. Okay, so remember we have delta H, enthalpy. I think I said entropy, I meant enthalpy. So this is either heat flowing in or flowing out. So our delta H tells us whether we're putting energy in or taking energy out. Okay, so if we have a delta H greater than 0, what does that tell us? So it tells us this is an endothermic process. In other words, we're putting heat in. Okay, so to go from a solid to a liquid, and I'm sure we all intuitively know this, but our delta H will be positive. Okay, and then if we put even more heat in, okay, now our delta H is still greater than 0, so we still have positive enthalpy. Okay, so we're still have an endothermic process. That's the word I was trying to find. Okay, and notice that the heat of vaporization is much, much greater than the heat of fusion. So it takes much more energy to change a liquid to a gas than it does to just change a solid to a liquid. Okay, and then what about if we wanted to go directly from a solid to a gas? That's known as sublimation. Okay, so we have fusion, which is melting, vaporization, which goes from a liquid to a gas, and then if we go directly from a solid to a gas, this is known as sublimation. Okay, we can also have, of course, the opposite of fusion, freezing. Okay, so these are exothermic processes. So, in other words, heat would be coming out of the material. So if we take a liquid and we, say, take water and put it in our freezer, okay, so the cold of the freezer absorbs some energy from the water to the point, and if it absorbs enough, it changes back into a solid. Okay, and then if we go from a gas to a liquid, condensation, so the opposite of vaporization is condensation. Again, we have an exothermic process. Okay, and notice our delta H of condensation, again, much greater than our delta H of freezing. Okay, so still it gives off much more energy to go from a gas to a liquid than it does to go from a liquid to a solid. So if you were in my class last semester, we talked about the steam, where the lady gets burned on her hand from steam. So notice going from a gas to a liquid, there's a big, big energy transfer there. Okay, and then if we can also go directly from a gas to a solid, this is known as deposition. Okay, so good to get to know these terms. So the opposite of fusion or melting is freezing, the opposite of vaporization is condensation, and then the opposite of sublimation is deposition. So this process is how you get freezer burn in your freezer. So water vapor sublimes into a gas and then deposits back down onto your food. Okay, so this is how you get dew. Okay, so condensation results in dew in the morning. Okay, and this, of course, we know is how you melt ice or something like that. Okay, so keep in mind the delta H for each of these. So we know that if we're going higher to a higher order of matter or to a higher level of disorder, might be a good way of looking at it. We know we have to put energy in. Okay, so remember, solid is our highest form of most highly ordered form of matter. It's hard to say. And then if we go from a low order or from high order to lower order, we put energy in. If we go from low order to higher order, we take energy out. Okay, so if we're going up in a phase, we have to put energy in. If we're going down in a phase, we take energy out. Okay, so generally the heat of fusion is less than the heat of vaporization for a given substance. And we know this because it takes more energy to completely separate molecules into the gaseous state than to partially separate them into a liquid state. So in other words, it's much easier to have things still intact, so just to melt something and then the molecules still have a lot of interaction and they're not having to completely break free. Okay, so when we actually vaporize something or boil it, those molecules actually have to completely break free from the substance. Okay, so that of course requires a lot more energy, and there's some examples here. So butane, you can see that that's still true. So 5 kilojoules per mole versus 24. So the purple is heat of fusion or melting, and the blue is heat of vaporization. So obviously heat of vaporization is going to be much higher in heat of fusion. So diethyl ether, very similar. Water, very similar. And then mercury. Look at the big discrepancy in mercury. Okay. So it always takes more heat, in other words, more energy, to cause something to go from a liquid to a gas than just to melt it. Okay, the last thing on, one of the last few things here. So heating curves. Okay, so a heating curve plus the temperature change versus heat added. Okay, so if we just take a look at this, okay, so we have basically what we're seeing here is actually phase changes. Okay, so if we start, so we're looking at water. Okay, so we know things like the melting point of water, the boiling point of water. But if we didn't know that, we could find them from this graph, and I'll show you how. Okay, so if we take a sample of water and say it's at minus 25 degrees C, okay, we know that at that temperature water would be ice. It would be solid water. Okay, and if we start to add that, or start to add heat, excuse me, if we start to add heat, okay, so our sample starts to go up in temperature, but nothing's happening. Okay, so essentially we're just warming it up. So from here to here, we're just warming it. Okay, and then we get to this plateau, where our temperature is not increasing anymore, but we're still taking energy in. Okay, so notice our x-axis is heat added, our y-axis is temperature. So here, we're not going up in temperature, but we're still adding heat. So what must be happening? We must be going through a phase change. Okay, in this particular case, we're going from a liquid or a solid to a liquid. In other words, we're melting. Okay, so our first phase change will be to go from a solid to a liquid. We know that. Okay, so that's our melting phase. And then we heat the sample some more. So we're putting energy in, temperature's going up. Okay, so warming again. But look what happens. We get to another plateau where we're still adding energy, still putting energy in, but our temperature's not increasing anymore. Okay, so this is the phase change for vaporization. Okay, then we have water vapor, and then we can continue heating it. Okay, so that's how you read these. So you want to look for these plateaus, and those indicate to you the phase changes. Okay, so if I gave you, for instance, just a blank heat curve with I just had temperature and maybe heat added labeled, and asked you to tell me where the melting point was or the boiling point of a substance was, you should be able to pick that out just based on knowing, okay, so I heat it, okay, then I plateau where the temperature's not increasing anymore. That must be the first phase change, and then etc. Okay, so the difference between where my temperature stops changing and I'm still adding heat, okay, that would be my heat of fusion. So the difference between this point and this point, that's my heat of fusion. Okay, so in other words, how much energy does it take to melt this substance? Okay, in this case, it's 6 kilojoules. Not so important to value right now. Okay, but being able to recognize how to calculate that. So the delta between, basically the delta H there tells you the heat of fusion. And same thing here. Okay, so delta H for my vaporization, so my heat of vaporization. Okay, notice again, it's much, much larger than it is for melting.